Hello, ladies and gentlemen. We're going to do 10.2 today. We're going to be talking about plane curves and parametric equations. Our objectives today are that we're going to sketch graphs of parametric equations. We're going to eliminate a parameter and write a different equation, and then we're going to find a set of parametric equations. Alrighty. Again, this is kind of like a time warp. We're going back to pre-calc, and we're talking about information that you learned in pre-calc. Okay, so I can add a third dimension to my equations. Sorry, an entertaining song just popped into my head. So it happens when you do this later in the day. All right, so the third dimension that we can add could potentially be time, or it could be theta, if I wanted to add a parametric of an angle of rotation. Okay, if we're going to talk about either of these, I'm only able to graph a plane curve, which basically means 2 dimensions, right? So if I add the third dimension, I don't want to graph in 3 dimensions. I still want to maintain a 2-dimensional graph. So I have to do some work to be able to generate those particular equations. And I'm going to need a calculator. Okay. Alrighty. So let's say I have a set of equations that define a plane curve. So let's say I have x is some function with respect to time, and y is a different function with respect to time. T is called the parameter. Did I spell it right? I did. T is the parameter, and both of these equations in terms of t work together with this additional parameter to create a system of equations. So it's going to create a system of parametric equations, and that particular system of equations is going to give you a 2-dimensional graph, and we call that a plane curve because planes are 2-dimensional because they extend in all directions but they don't have thickness. There's a crash course in geometry. So let's talk about ways to sketch these if we're looking at our parametric curves. So let's say I had a system of parametric equations and I had x is equal to t squared minus 4, and I had y is equal to t over 2, and I want to consider negative 2 for time less than or equal to 3. Let me scoot it up so you can see. And if you'll remember, what I told you to do in pre-calc, and I know that was a long time ago, was to never do this math by hand. So we're going to use our calculators to generate a table. So now that you have those equations written down, I'm actually going to cover them up because my calculator looks better on this side. So we'll turn our little guy on. I'm going to go to my mode button, and I'm going to put my calculator in parametric mode. And just because I'm going to put it in radians, I don't need to, but I'm going to. And when I look at my y equals, oh look, there's already some parametrics there. Notice that I have 2 equations instead of 1. So I have x sub 1 with respect to time, and I have y sub 1 with respect to time. So if I entered, I want to enter this one first, and I did t squared minus 4, and then on this equation we had t and then divided by 2, and then I'm going to go to my table set, and I'm going to tell it to start at a negative 2. I'm going to tell it to change in ones. I want it to be on auto, and then I'm going to go look at my table, and miracles occur, and notice that even though I have 3 variables, it's generating a table of values in terms of x and y, and then this is my additional parameter. Okay? So since I'm graphing a planar curve, I would only graph my x and y, but it's tricky because I want to show the other points that are in there. So I'm just going to do a few of these. So to show you what we would do to draw an accurate graph, because I can't draw a three-dimensional curve to show time, but I can show the progression of time. So if my first point was a -2, my x value is 0, and then I get a -1, so that's a -1. And then I'm going to go out to, and I'm just graphing a couple. I'm going to go out to a -4 for my x. So 1, 2, 3, here's the -4, and that value is 0. But when I did my graph, I moved from here to here, and so I missed, sketch my curve, and I need to show an arrow to show the progression of time. Well, then if I get over to 0, I have a y value of 1, so I would make a really crappy graph. It's going to go back this way. And so I would continue to plot those points to show the progression of the time. And the only way that I can do that in a two-dimensional graph is by showing the arrows in which direction my time is traveling. All right. So that's actually really simple. So I can graph a set of parametric equations, look at the graph, and I can follow the progression of the graph. Okay? So the next thing that we want to do is we want to eliminate a parameter and then rewrite the equation. All right. So let's say I've been given x is equal to t squared minus 4, except you can't see it. Sorry, my bad. And I have y is equal to t over 2. And I want to eliminate the parameter. Okay, well, the additional parameter in this particular equation is time. So I'm going to solve for t, and the process is always the same. So I want to solve for t, or whatever the additional parameter is, in the easiest equation, because why would I make my life any harder than it needs to be? And then I'm going to substitute back into the other equation, and then, ta-da, now I have eliminated and have a nice equation. So if I do this particular problem, let me turn this on, because sometimes when I don't, then I do stupid math, and that just makes us all sad. So if I solved for t in this one, I would cross multiply, so I would get t is equal to 2y. I'm going to substitute this into this equation up here. So then I'm going to have x is equal to 2y quantity squared minus 4. Typically, we would solve for y, so I would get 2y squared is equal to x plus 4, and then I'll come up here since I'm running out of room. Y squared is equal to x plus 4 over 2, and then y is going to equal plus or minus the square root of x plus 4 over 2. So just like other math that we've done, you would stop wherever it's relevant for whatever application you're doing. Okay? All right. I think that's kind of it for that part of it. I could do another example for eliminating the parameter, but at this point I don't know that I need to, because the process is always the same. I'm going to solve for t in the easiest equation, substitute back into the other equation, solve for y, ta-da, done. Okay? All right. So then let's look at a problem. Actually, I lied. I want to look at a problem with polar coordinates. And we have not done polar coordinates in a very long time. Okay, so I'm just going to give you a quick crash course in polar coordinates. So polar, remember, is when I get to do those really fun graphs where my graph paper is circular. I have ordered pairs that are theta. Remember, when I plot a point, I do theta first, and then I manage the radius. Okay, so if I had, we'll just go ahead and do this one right here since I have one. So let's say, get my cute little graph paper in there. Let's say this is pi over 6, and I had the point 3 pi over 6, and I wanted to graph that point. Well, I do the angle first. Here's pi over 6, and then I have 1, 2, 3 for the radius. So there's the point 3 pi over 6. tricky thing to remember is what if I had a negative 3 and then pi over 6? Let me get a different color. Sorry. So we'll do this guy turquoise. I always graph my angle first, but in polar coordinates, I can have a negative radius, and the negative radius pops me 180 degrees to the opposite side of the circle. So if I graph this one, here's the angle, but the negative radius would take me to 180 degrees across the circle, and so that would be this guy. Other things that you need to remember about polar coordinates, even though it's been a million years, I have some conversion factors. X is going to be r cosine theta, and y is going to be r sine theta. I use the Pythagorean identity x squared plus y squared is r squared. Sorry, that's my equation of the circle. And here's the identity. Sine squared theta plus cosine squared theta is 1. So that's really what you need to know as we go back and do polar coordinates. I can convert the equations back and forth, so depending on the problem depends on the approach that I would take. So let's say you're given x is equal to 3 cosine theta and y is equal to 4 sine theta. Again, that's a 3, sorry. Remember, anything that we do in our calculators when I'm graphing angles, I want my calculator to be in radians. And we're going to talk about one full rotation from 0 to 2 pi. So in this particular problem, I want to sketch the curve. I want to eliminate the parameter. And then I want to find the rectangular equation. Alrighty. Okay, so let's sketch it by putting it in our calculator just because I think that would be kind of cool. So let's see, do I have a picture of that? I think I do. Let's try this and see what happens. So let's take this off and this off. And let's go in and put 3 cosine, and I'm just going to put, except it goes up there, 3 cosine t, because it doesn't really matter what my variable is. And then I'm going to do 4 sine theta, except I'm going to have t's, and I'm going to do graph. That was pretty cool. Alrighty, so if you watch that, let's do quit, and let's see, can I get it to draw it again? Oh, sad day. But because I haven't done this in polar coordinates, it actually turns out to be a little bit odder looking. But really what we have is an ellipse. We just needed to change our window so that we're getting a nice smooth curve. But the chunky curve actually looked kind of cool. Notice that I have 3 on the horizontal axis and I have 4 on my vertical axis. It's just kind of hard to see. Alrighty, so let's go ahead and convert and eliminate our parameter. So if I start with my equation here and I solve for cosine theta, I'm going to say the cosine of theta is x over 3 because in this one, theta is your parameter. So that's the guy that I need to eliminate. And then I'm going to have the sine of theta is y over 4. But instead of eliminating, I'm going to take this information and I'm going to substitute it into this equation right here, which is my Pythagorean identity. Okay, so I'm going to say x over 3 quantity squared plus y over 4 quantity squared is 1. Well, look, now it's the standard equation of an ellipse, and I would write this as x squared over 9 plus y squared over 16 is 1. So we sketched the curve. I cheated and we did it in our calculator. And then we eliminated the parameter, which we took away the theta, and I wrote a rectangular equation. So that was kind of cool. Alrighty. So all of those things apply. Another thing that I want to talk about is just another way to see this equation just for some information. So let's say I have x is equal to h plus a cosine theta. Make it where you can see it, I'm sorry. And then y is equal to k plus b sine theta. And I go from 0 to 2 pi. This is going to be the same thing as x minus h quantity squared over a squared plus y minus k quantity squared over b squared is 1. And the book said that this would track clockwise. So that means that as we move around the eliminated parameter, which in this case is the angle, it would move around the circle in a clockwise fashion. Alrighty, I have one more example. Is that true? That's true. And then I have just kind of a little bit of information about some cycloids, which is cool. And we've seen that information as we've moved along. All right, so here's the next example. And we want to find a set of parametric equations. So we're starting in the opposite direction this time, where we're going to try to create a set of parametric equations that represent the graph of y is equal to 1 minus x squared using the following parameters. So we're really going to do the problem twice. Okay, so in A, the parameter that I'm going to use is t is equal to x. And then we're going to do the problem again, and we're going to say that the slope, remember slope is m, is going to be dy dx. There's a little bit of calculus at the point xy. All right, so let's do A first. Okay, so I'm starting with y is equal to 1 minus x squared, and they're telling me that x is equal to t. Well, to parameterize, that's a hard word for me to say, the equation, really all I have to do is substitute this information into here. Alrighty, so if I do that, I'm going to get y is equal to 1 minus, and then x is t squared. Well, my system of parametric equations is going to be x is equal to t, and y is equal to 1, oops, that's a 1 minus t squared. And this is my system of parametric equations. Well, that didn't take very long. All right, so now let's do the B part, which is just a wee bit more fun. Not much, but a wee bit. So remember that slope is equal to dy dx. So I'm going to take the derivative of the original equation. So I'm going to get that my slope is equal to a negative 2x, okay? And that is the derivative of my original equation. So my dy dx is a negative 2x. And I know that this is going to equal m. So now what I'm going to do is I'm going to solve this equation for x. So I'm going to get x is equal to a negative m over 2. Well, now that I know an equation for x, I can substitute that back into my original equation. There it is. So if I have y is equal to 1 minus a minus m over 2 quantity squared, that turns out to be 1 plus m squared over 4. So my system, and again, this is really super simple, is going to be x is a negative m over 2. And then my y is going to equal 1 plus m squared over 4. So really not a difficult process at this point. And I'm sure it will get to be more entertaining, but so far so good. Alrighty. The last little bit of information that we want to talk about is a cycloid. And I will have a fun little video, I think. Is this the one where I have a cool video? Yes, this is the one. I have a really cool video to show about an application of this. But a cycloid is a rolling curve. So when you guys come to class the next day, we will talk about these cycloids or the rolling curves? Well, they look like this. So I might have a situation, I never draw that axis long enough, that looks like that. Well, Galileo used these to talk about arches and bridges, which means then we get to start doing some calculus on those guys. And then Pascal used these to talk about the area under an arch, and then he talked about the volume of the revolved solid. And all of that information was used as the ancients were creating the work to build bridges and arches and support massive structures. So I think that's really cool. So I'm going to continue just a little bit with our cycloids. Okay, so scoot this up. We have a generic equation, x is equal to a times theta minus the sine of theta, and y is going to equal a times 1 minus the cosine of theta. And these would be the system of parametric equations that talk about our cycloid. Okay, so that's all I'm going to show you today. We're not going to do a lot with these. Another thing that might be interesting to talk about before we watch the movie is that if I were to try to take the derivative at these guys, you would tell me that's not possible because it's a sharp point or a cusp. I hate that word. I think it's a weird word. But we also know that the curves are continuous in between these sharp points, and they're differentiable. So since they are differentiable and continuous in between, then we would say that there are smooth curves in between that generate your cycloid. Alrighty, that's it for today. I will see you tomorrow, and then we will watch a cool video about cycloids. See you soon.